So, hello everyone, and welcome to Conversations on Ichnology. The International Ethnological Association is glad to offer this lecture series to anybody interested in ethnology. The lectures will be held on the last Friday of each month until November and made available in the IIA YouTube channel. Thank you for joining us today, and thank you to all IIA members who support our organization. If you are not already a member, we invite you to visit our website and join the IIA. But our special thanks today go to Dr. Shillito, who gently agreed to be the keynote speaker for this month, discussing true substrate and their role in the paleobiology of trace fossils. Anthony Shillito received an undergraduate degree and a master in science degree in natural sciences, focusing on geology at Cambridge University, and then a PhD supervised by Dr. Neil Davis, who provided his first introduction to ichnology. After that, he spent 3 years at the University of Oxford as a junior research fellow, working on understanding changes to life environment interactions during the initial colonization of land. In 2022, Dr. Shillito moved to Canada on a 2 year Benting postdoctoral fellowship with Drs. Luis Botois and Gabriela Mangano at the University of Saskatchewan and have been there since while searching for a permanent position. His work mostly focuses on animal sediment interactions during the Paleozoic, but also he has also an interest in how time is preserved in the rock record and how that affects how our observations are interpreted based on this record. This talk will be recorded, so I gently ask you to close your microphones to prevent noise interferences. And Anthony, you have the floor.
Great. Thank you very much, Renata. Right. Hopefully that has all appeared nicely and ready to go. So yeah, thank you for inviting me to give this talk. It's always great to be able to talk to members of the ecological community. Yeah. So today I want to talk to you about essentially time in the rock record and how that relates to ichnology. I'm going to do that with a focus on bedding planes. I'm going to spend the first part of the talk possibly being a little bit more sedimentological than people were expecting, but then we'll introduce a couple of case studies and talk about how the ichnological record can provide some really useful information that isn't normally considered when people are trying to understand time. And then something which those of you who attended ICNIA last year might be familiar with, talk about how outcrops broadly affect the kind of observations that we can make and the quality of those observations, and then how we can account for that. So to begin, time in the rock record is typically viewed as the record of deposition. People were saying, okay, you've got your big pile of sediment left, the sedimentary rock, that's time, and everything that's not recorded as deposition is missing time. And I would quite like to provide a counterpoint to that and say, actually, depending on which depositional environment your rocks were formed in, that's not necessarily the case. And a lot of this so-called missing time can be observed as recorded in other ways during sedimentary states that aren't deposition. So here, just to get some field photos in off the bat, we have the Tumbleguda sandstone of Western Australia, of the Battery Point Formation from Gaspé in Quebec, and the Yamat Formation from Mongolia. All of these we have, these big piles of sediment, but all of them were interpreted as being deposited over millions of years. And that isn't just accounted for by the record of deposition. Deposition is occurring in events and over short time spans. So what is happening the rest of the time? How do we fill in these gaps in time? That is by considering the other sedimentation states. So deposition, really very important, but we also need to consider erosion and the topic of this talk, sedimentary stasis. So stasis is when we're getting neither deposition or erosion. It can occur alongside transport. And this is when a lot of life environment interactions are occurring. And this is kind of illustrated with the Shillito diagram, which shows that for any given particle, any given flow velocity, the energy of the system we're in, we're going to be getting particles of some size transported. So the substrate will be in stasis, we'll be getting erosion, we'll be getting deposition. And how do these sedimentation states relate to the rock record, right? To the product that we're getting, what we're actually looking at, what we're basing our observations on. So this, here is some work by Zoltan Silvestri and others from last year now. And it's some experimental flume data that they produced. I've just put this up to kind of illustrate how little of the preserved time in the rock record is made up of deposition. Here we have, for example, where you can see the 0.205 here. So about a fifth of time is deposition, 10% just over is erosion, 40% in this example is stasis, and then vacuity is where we've had deposition or that's then subsequently been removed from the record by erosion. So yeah, there's a lot of time that's in the record that isn't being recorded as deposition, it's being recorded as something else. And here, just to show how this varies between different depositional environments. And again, this is from their flume study with A through to D getting increasingly distal. So A corresponds closely to a fluvial type environment where we've got very limited accommodation space. So we're getting deposition, but we're also getting lots of erosion and we're not getting very much sedimentary stasis. You can see that by the proportions that we've got recorded up here, where maybe 50% is recorded deposition plus erosion. We've got a whole load of deposition that's been removed and very small proportion is stasis. But as we get more and more distal, as we get into deeper water deposits where accommodation space isn't such a restricting factor anymore, stasis becomes more and more significant, and durations of stasis also increase. And the length of these, how durations of stasis varies, something that I'm going to talk about and what that means for our observations and interpretations of ichnology. So this is a big bedding surface from the Tumblr sandstone, and you might look at it and think that is an erosive surface, nothing to see there. But this is actually a record of sedimentary stasis. And when you look closely, you see cross-cutting many of these facets, you have little burrows and trails. And when we observed this, when I was out in the field with Neil Davis in 2016, and we saw this, thought, this is a little bit odd. How do we account for this? What does this mean about time in the rock record? Why are we seeing this? And we came up with the term true substrates to describe and explain what we're seeing. So essentially, describe a true substrate as a sedimentary bedding plane that demonstrably existed at the sediment water or sediment air interface at the time where it was deposited. And this is evidenced by the features you see on the bedding surface. So it's essentially a highly accurate fidelity bedding surface is a snapshot into the time of deposition. It is recording something that was as it was when it was formed. And along with a whole group of co-authors, some of whom are in the listening to this talk today in the chat, we put together a volume that's come out this year on bedding surfaces, specifically leaning towards true substrates and Earth historical archives. So how time is preserved in the record and how the record of sedimentary stasis recorded as bedding planes and true substrates provides a load of information that we just can't get from looking at sediment piles alone and thinking about the deposition or record alone. So what conditions do we get these true substrates formed in? And it really depends on the sequence of sedimentation states that we see. So, as I said, we have our deposition, erosion, transport, and stasis, and transport can occur alongside any of the other three. And if we're just seeing continuous deposition, DDD, we're not going to see any kind of true substrate. We're just getting this thick sediment pile that builds up. We might get erosional surfaces in there, the DDD. But once we get some stasis involved, either through deposition, but stasis deposition, or something like deposition, erosion, stasis deposition, we have surfaces that were colonized by life, if we're looking at the Paleozoic surfaces that can be colonized by life, or can have physical sedimentary structures formed on them, that then provide this true substrate, this snapshot into the instant where it was formed. And that can tell us about the day-to-day activities or what it was like at this given point in space and in time. Get some confusion introduced when we get erosion added in. So if we have stasis followed by erosion rather than stasis followed by more deposition, then we get maybe truncated burrows or something like that. So it's not true substrate, but we're still seeing evidence of that bedding surface that was there. And you can see from here that you can combine multiple different sedimentary states, and you might get multiple generations of burrows appearing on the same surface, which can be hard to disentangle. But essentially, we're looking at, when we get stasis followed by deposition and the snapshot that can provide us on deep time. So how much this missing time do true substrates account for? And the answer is really, it depends. It depends on a whole host of factors. Where within a broader depositional system this true substrate was, what the environment was. And often we're not going to be able to know exactly how long it was, but we're going to be able to get ballpark figures. And here we have just a couple of examples from Cambrian, Potsdam Sandstone, Ontario. These are thought to be some of the first subaerial animal tracks. And we have this from the Carboniferous Bude Formation in the UK, which are thought to be some deep lacustrine deposits, where again you have afterward tracks, and you also have some Undicna fish traces. And these two are likely fairly different durations of time. If we're getting infrequent deposition in our deep lacustrine deposit, we may have a long duration true substrate here, whereas in an Aeolian dune deposit formed on a dune face and a slip face of dune, this may just be more transient. So we're seeing much shorter time frame. The timescales of true substrates are typically on experience timescales. So essentially the kind of time scale that an individual experiences over their lifetime. And this makes them relatable, and it also means that they're useful for understanding life environment interactions on the life scale of animals. It also means that there are some phenomena that are just not going to capture true substrates, capture embedding planes. There are also some phenomena we're not going to be able to capture in individual outcrops. Anything basin scale, anything that's occurring over much longer time periods. That doesn't mean that there isn't a whole load of really useful information that we can get here. So this is just a few different examples from the key paper in that publication I talked about earlier, where we look at both physical processes here, biological processes, and weather type processes. You can see essentially from the physical processes, true substrates aren't going to record a lot on a kind of tectonic scale. We're not going to see examples of like a snapshot of an orogeny in one bedding plane. That's just not going to happen. We're not going to see isostatic rebound or plate tectonics. But we can see short-term, like rapid events. We have this earthquake bed from the Maritimes of Canada. On, sorry, biological processes, we're not going to see anything, we're not going to see evolution from a bedding plane, but we are going to see animal environment interactions. We're seeing bioturbation, we're seeing burrowing. In a weather type processes, we don't see Milankovitch cycles, we're not seeing glaciation occurring in an individual bedding surface, we're not seeing a monsoon, but we might see a storm or raindrops, and here again we have drip impressions. All of these from the Tynemouth Creek Formation of New Brunswick. So we have an idea about the time scales that these true substrates occur on, and the kind of phenomenon that we might be able to observe from looking at them. But in order to better idea of how we can use them, how we can use bedding planes in general, we also need to consider where we're going to see these true substrates within broader systems and how the durations of stasis is going to vary within systems, because many sedimentary systems are extremely laterally heterogeneous. So might get energy conduits within these systems. So here using a fluvial example, that are high energy, and then regions detached from these conduits, regions between them, that are low energy. So again, using a fluvial example, we might say our energy conduits are the channels. The regions detached from them are floodplains, where typically they're low energy apart from infrequent events. And in any sedimentation event, energy is going to wax and wane within a system at any given point, and that will lead to changes in the sedimentation state from deposition, stasis, and erosion. And that relates to this plot where we essentially have a waning flow that will erode the area closest to a point source. As we get further from the point source, as energy dissipates, we see stasis, and then deposition furthest away as the energy drops to the point where we're then depositing all of the sediment. In high energy regions within the system, we're more likely to be experiencing deposition or erosion. As we see in fluvial channels, we're getting constant movement of sediment, we're getting constant deposition, but it's also being constantly eroded. And in low energy regions, such as our floodplains, we're far more likely to be seeing sedimentary stasis. And this means that our high energy regions, high energy facies, are having far more frequent events, but we're also getting less time completeness from these areas. Whereas our low energy facies, low energy regions of depositional settings, we're seeing less frequent events, but we might get far more time completeness in the form of stasis because we're not getting this frequent erosion. And considering now just another plot that illustrates how that varies within a system, So A versus B here. A is representing an unstable system, such as a pre-vegetated fluvial system, where at 3 different points within the system, you're not seeing much variation. We're seeing lots of switching between deposition and erosion and stasis, but there's not a clear difference between any of these points because our channels are migrating all over the place. We're getting deposition, erosion, and stasis everywhere. In a more stable system, such as Artesian vegetation, our modern meandering fluvial systems, things we've been seeing since the Ordovician, we get far more differentiation. So again, within the channel, within the high energy regions, we're seeing this fluctuation at any given point between deposition and erosion with very little stasis. And any stasis that's occurring is almost instantaneous. As we get a little bit further away, maybe we're close to the channel, but not in it. We're getting infrequent deposition and erosional events with floods, maybe overtop or crevasse splay deposits. But the majority of the time is stasis. And then as we get further away still, the most distal regions of the floodplain, stasis makes up the vast majority of the time, and deposition is only occurring infrequently. And that really affects what we're going to be able to see in the rock product and what a bedding surface means in each of these different environments. If we look at a bedding surface that has a trace on from within a fluvial channel, that's an instantaneous snapshot. That's a very short period of time that is telling us about. Whereas if we're looking at a bedding surface at top of a paleosol on a distal floodplain, that could be recording hundreds of years of life environment interactions. So it's a more muddied signal. It's telling us something a little bit different. This is just illustrating these variable durations of stasis within the system. So if we see the difference between kind of instantaneous stasis, this single depositional event, like we're seeing in these fluvial channels where, yeah, you don't record very much time. As you increase the duration, as you get to hours to weeks, then you have more time for life environment interactions. You're more likely to see burrows either from a single generation or multiple generations. You might see trackways that occurred days apart recorded together. But it's still giving you an idea of a community that was inhabiting the same space at approximately the same time. As you go to months or years of stasis, you start to see higher order sedimentological signatures and things that require much more longevity. We might see more evidence of roots or plants growing. And this is when we start seeing life signatures that may not be co-occurring together. As we get longer still, you see this more biogeomorphic landscape, but bedding surfaces get more degraded as we get more plant interaction, more chemical modification of the substrate. Things degrade and older signatures get overprinted and replaced until eventually we get lifespans of stasis that we're not going to observe in the rock record, where everything has been overprinted and gone, and we don't see any original signatures anymore. Now, stasis varies dramatically between different depositional settings, and I'm going to show a couple of them as case studies in a couple of slides' time, just to give an idea. A is from all of these are schematic sketch logs illustrating different depositional settings. So A is based on the Hangman Sandstone of the UK, which is Playa Lake and fluvial deposits. You can see very few true substrates, which are marked by red, and bedding plains and the fluvial deposits, far more in the lower energy environment where we're seeing more stasis. In a true lacustrine formation, diabag formation, again, we're seeing this high frequency of true substrates of sedimentary stasis. So we're seeing a much higher, greater time completeness because we're seeing far fewer erosive events. The delta front, the Yarmat formation, and we see infrequent true substrates and less time completeness because we're getting constant deposition within this conduit a lot of the time. And the Tumbler-Gouda sandstone tidal flat type deposits, we see lots of true substrates that may be of hours to days duration. Now, before I get on to the meat of the talk and the ichnology portion, I'm going to talk quickly about the caveats of all of this, because as you can see from looking at the size of these circles as they progress, we are getting a vanishingly small fraction of these original snapshots preserved in rock record. If you think about the original population of ripple marks that form on a beach, the majority of those exist for seconds. They're transient during motion of the ripple. The fraction of those that then, are in stasis on the substrate after the flow's gone, many of those are subsequently destroyed. Then of the ones that are interred, some are reworked, some are destroyed by bioturbators. Of the ones that are then lithified, some are lost by post-lithification erosion, some are destroyed by diagenesis or metamorphism. Few are preserved to the present day, and many of the ones that are preserved are hidden within the rock strata. So the number that actually crop out as true substrates is very small, but that doesn't mean that it's not an accurate representation of time at that specific point where they were preserved. So the part that people may have been waiting for is, where does ichnology come into it? Well, trace fossils are often produced during sedimentary stasis rather than being produced during active deposition or active erosion. And lots of trace fossils that aren't produced during sedimentary stasis are going to be lost due to erosion. So the ichnological record can be really useful for filling in some of the missing time that occurred during stasis, because we get an idea of what was happening at that point while deposition wasn't occurring. We can see how life interacted with the substrate, and that's recording that time in the rock record. And different durations of stasis in different depositional environments mean that different ichno assemblages will tell different stories. If we've got short durations of stasis, then we're getting a snapshot of a second, a minute, an hour of what animals did in a short time frame together on a bedding surface. Whereas our longer time frames, we might get a palimpsest. We might see how communities changed over a month, a year. So having an idea about duration of stasis really helps us to make better interpretations based on our observations. So the first case study I want to use here for different durations of stasis and what it can tell us is the Jurassic Lastres formation from Asturias in Spain. And you can see this as some nice cliffs where we've got deltaic deposits. To give you an idea of the depositional settings that we see, we broadly have we're deposited as a delta. So we have the proximal delta plane deposits where we're seeing floodplain, crevasse splay, proximal distributary channel. So we get into the distal delta plane, we get some interdistributary bays, we get some more kind of closed ponds, we get marshy and more channel, and we have our delta front and our prodelta. So looking at the proximal delta plane, here we have the longest durations of stasis occurring furthest away. So here, bringing back this plot just to highlight things, A and B record our paleosol deposits where we've had extremely long durations of sedimentary stasis, and bedding surfaces, such as you see in A, are really quite degraded. We do have a sauropod track here. It's lots of calcretes, but there's not a huge amount we can tell about exactly what was occurring on that bedding surface, other than that sauropods were traversing this area of the delta. So you look at crevasse splay type deposits where you have potentially shorter durations of stasis. We're much closer to the channels. We are seeing, again, a palimpsest of traces. Not all of these burrows necessarily occurred at the same time, but it's a better snapshot of animals that were more likely living together. And here we have an example that's likely a much shorter duration of stasis, where we have some theropod footprints marked by the white arrows, as well as some plant material in black, some arthropod tracks in gray. But again, we're getting an idea of what the community was from these intermediate durations of stasis. And then E and F are fluvial channel type deposits. So this is a point bar where we see a selection of dinosaur footprints, and then F even within the channel itself in soupy sediment, where marked by the white arrow, we see this dinosaur footprint. And this is because durations of stasis in channel likely extremely short. This is just providing us with a snapshot of the activity of a few animals. It's saying the story we can tell from this is a dinosaur was walking near the channel, possibly within the channel, and it walked up the bank. So again, it's different stories based on different durations of stasis. Distal delta plane deposits, again, we have different durations of stasis. We have hours to possibly days, depending on how frequently tides were occurring or where we were within the system. In the intradistributary bays, and here is where we're seeing lots of animal environment interactions, whereas longer durations of stasis are occurring in the marshier deposits, are bog type deposits. And finally, the delta front, we get long durations of stasis recorded by our transgressive deposits. So we have essentially ring transgression, the top, and this shell lag forming and infilling some burrows. And we also see shorter durations of stasis on the delta front, again, likely affected by tides. You can see some ladder ripples. And the interdistributary bays record some great true substrates that can provide us with detailed snapshots of animal environment interactions over fairly short timeframes. So this is possibly my favorite example of a true substrate from anywhere in the world. As we see the trace, the recently described trace, Cumulus cygnus astoriensis. And anyone that's been down to the beach and seen logworm fecal casts will recognize this. And it is, in my mind, incredible that we can see exactly the same thing in the rock record. See this high resolution record of something that occurs every day at the beach. Here we have Cupicnium tracks moving across the bedding surface. And here we have some kind of tadpole nesting ripples with organic material in the troughs and evidence of animals going across and feeding on it. So again, our true substrates here are just providing brief snapshots of everyday life in these environments and showing how different points within the broader system were experiencing different life environment interactions. But I'm going to put up this plot to show that actually we're not necessarily seeing direct correlation between either ichnodiversity or bioturbation intensity with duration of stasis. So just because we've got longer period of time for traces to be formed doesn't mean that we're going to see more traces or we're going to see a greater variety of traces. There are more factors at play, and it's not that straightforward. So A here just shows the different sub-environments in a little bit more detail. I talked about in the first slide. You can see here that mapped out with the stasis duration. So as expected, the greatest durations of stasis, prolonged stasis, will be occurring on our floodplains, our crevasse blade deposits, and our closed ponds, so our marsh type deposits. Far shorter durations occurring in our intertributary bays, where it's maybe just hours to days, and shorter still in channels where it's more instantaneous and off the delta front. You can see here that despite shorter durations of stasis, we're still seeing far greater ichthyodiversity and bioturbation intensity in these shallow marine type deposits. And I think it's important to recognize that, yeah, whilst stasis is important, it's not everything. The environment itself is still extremely significant. And if you don't have the right conditions for animals to be interacting with the environment, like in our marshes, which may be more anoxic, you're still not going to see ecological signatures that are informative. We get no biodiversity there at all. Our second case study is the Tumbleguda sandstone from Western Australia. And this is probably my favorite field location in the world. And if anyone gets the opportunity to go out there to look at the trace fossils, I would highly recommend it. It is fantastic. You can see here we have a few trackways on this bedding, on this loose block, along with this large burrow. So the Tumbleguda sandstone is deposited mostly intertidally, but we also see fluvial channel that kind of transforms into more estuarine deposits, and then we have the offshore. And just to give an idea about the different colonization or the different niche occupation in these different areas, as we're back in the Silurian, nothing's living, or there's no evidence of anything living in the fluvial channels. We see fairly low diversity in the estuarine deposits. You see there's high diversity in high disparity on the tidal flats, and low diversity again, but high density of traces occurring in shallow marine deposits. And again, we get different insights from the different durations of stasis. So here we may be getting greatest durations of stasis occurring in our subtidal deposits, where we may have more stability of the dunes. They may not be moving outside of more significant events. And so we get lots of vertical unbranched burrows of animals that may be inhabiting these substrates for a longer period of time. We also get a lot of palimpsesting of traces occurring here because of this greater duration. We get many true substrates from the Fascia Association 2 when we have hours to days of stasis, and I'll show them in the next couple of slides. Again, fluvial deposits uninhabited, and then very short durations of stasis in our FA3, our kind of estuarine type deposits, where we're getting constant movement of these bar forms and opportunists colonizing them. And quickly looking at true substrates from a couple of these to tell you what they can show and how the different durations of stasis recorded on different true substrates lead to different information. So this here is from our tidal deposits. And you see at the top, we have adhesion marks, then we have a smooth slope and some ripples in the bottom. And this is interpreted as a pond where essentially an arthropod has walked along the top and dislodged this piece of adhesed sand that's then slid down the slope. So again, it's providing us with just a little snapshot of the everyday activity of an animal that was living in the area. Here we have another true substrate that has some original topography preserved, these small ponds. And you can see, if you look closely, evidence of animals moving in and out of these ponds. So we don't necessarily know that this was all occurring at the same time, but we know that these animals were occupying this area reasonably close to each other. There wasn't a huge time gap between this arthropod walking into or out of a pond and this one, or the larger animal traversing the substrate. And finally, the true substrate that I showed earlier, which is from this estuarine facies from the Tombaguda sandstone, where we have opportunists that have colonized this surface following a period of erosion, and they're scouring it for nutrients before the next flow is coming in and burying. So for the last part of the talk, because I realize I have waffled a little too long on some subjects, I want to talk about why outcrop morphology is important. And you'll see how this relates to everything I've said so far, because I'm going to keep harping on about lateral variability within environments. And you can see an example of that here from a modern beach. This photo was actually taken on the inter-conference field trip at ICNIA last year, where you can see essentially slight variability in the sediment means we see the animal track of a crab that was walking across the sand here, and then suddenly it disappears as the sand changes. And this variability in biotopes, so variability in our environmental conditions within broader depositional settings, leads to a variability in the ichnological record. And whilst you might see a high density at one spot, if you walk 5 meters even along an outcrop, you may get a fairly different signature. And this is highlighted nicely by a study that Duncan McElroy did almost 20 years ago, looking at the Lower Jurassic of Yorkshire in the UK, where essentially he followed the same bed along the coastline and looked at the ichnofabric in that bed and the relative abundance of different ichnotaxa. You can see that it varies dramatically. So if you just looked at one point, you would get a very different idea of the ichnological makeup of that community than if you went a little further down the coast. Compare BH11, for example, with BH3. Suddenly you've had this huge jump in tachicnus because conditions favored tachicnus at that given point, and this large drop off in phycocyphon. So if we have extensive outcrops, you can see this, but if we have small outcrops, you don't get to see this lateral variability. You're just making do with what you see from one given point. You're getting a small part of the story. And it's important to make that clear in your studies so that people are aware of the possible information that's missing. We also see similar variability from the Leaness sandstone in the Cretaceous of the UK. And here, this is with dinosaur footprints, where we see areas where you get high density of dinosaur tracks, and then you get tracks with very few footprints that are preserved. And again, this means that without being able to see this long-term record where you can see areas with and without, if you look at the wrong spot, you might assume there was nothing there. And the final example, a study by America and Hagedorn looking at the Elk Mountain group in Wisconsin in the USA, where you get some really large bedding surfaces, gives you a great idea of just how variable things are. So this plot essentially shows the variable abundance of either Gordia or climatic 90s, depending on which site, across these large bedding surfaces. And because you've got a large bedding surface, you can see this variability. You see areas where they are highly abundant and areas where they're absent. But if you're looking at an outcrop that has a small bedding surface, you don't know which part you're going to get. You don't know if you're looking at an area where it's dense, if that's representative, or an area where it's absent, if that's representative. So recording characteristics of the outcrops that you're working on is really important for understanding what our observations mean. So how can we account for outcrop in our work, in our studies? What can we do to make it clear so that these studies are replicable and people know what our observations really mean? So with Romain Goujon, we built on some previous work that both of us had done to build a scheme that essentially accounts for variability within the outcrop and how different outcrop morphologies can lead to preferential observation of either vertical or horizontal trace fossils. And this is important as to also include extent of the outcrop that you're looking at. So if we're seeing more extensive bedding planes and less extensive vertical sections in the outcrops we're looking at, this definitely favors observation of horizontal trace fossils rather than vertical. We will get some idea of vertical from cross-cutting, but less. Whereas if you're looking at more cliff type deposits, you're really missing out on any horizontal signatures that may be occurring. And just to provide some examples of that, again, from the Tumblr sandstone, RI here is relative ignodiversity of vertical traces in blue versus horizontal traces in red. So here, our big extensive plateau type deposit, we are favoring observation of horizontal traces, but you do see vertical as they cut down through the beds. With our stepped type outcrop, where we see a relatively equal proportion of bedding surfaces and vertical sections, we can rely on the signature and assume that it is fairly accurate, that if we're not seeing horizontal trace fossils, that's because they're not present. Whereas here, where we strongly favor observation of vertical traces and don't see any horizontal, that could just be due to bias of the outcrop. Whereas here, again, we're seeing a step type exposure and we see high diversity of both horizontal and vertical. Finally, we also need to account for structural effects and superficial cover. So it's important if you're looking at a cliff like we're seeing in A here. This cliff is actually a bedding surface. These rocks have been rotated 90 degrees, but it's still a stepped plateau type deposit. Again, here, this is a stepped type deposit, but it's been rotated 90 degrees. And here, even though it has been rotated extensively, it's still a cliff type deposit. It's just rotated. So again, this is still favoring observation of vertical versus rather than horizontal traces. Just everything has been rotated. It's important to account for superficial cover because it strongly restricts the observations that we can make. We don't know what's happening underneath the snow. If you're making your observations in winter, you might see something very different to making your observations in the summer. Again, that's an issue with either cover on beaches, where the beach may be lower in the summer than the winter, so you may see more exposed outcrop on the foreshore, or with vegetation growth, where again, things may die back in the winter and grow extensively in the summer. So to conclude, to say that True Substrates record sedimentary stasis, and they show that the rock record is more time complete than we often assume. Ichnology really helps to fill in this gap, and it can tell us how animals are interacting with their environments during time that is often considered to not be preserved. Durations of stasis vary dramatically by depositional setting as well as within sedimentary systems. And we've got to take this into account when interpreting our observations. Are we looking at a snapshot that lasted 10 minutes? Or are we looking at a bedding surface that's recording 10 years? Because we should interpret interactions between the traces differently depending on the duration of stasis. And then finally, all observations are controlled to some extent by the morphology of the outcrops from which we're making these observations. And so we should be reporting outcrop style, morphology, quality, and cover whenever we're reporting ichnological observations, because all of these factors affect the observations that we can make and how representative they are of the formation as a whole. So with that, I want to thank all of you very much for listening to me talk, and be happy to take any questions and have some discussion. Thank you very much.
Thank you, Anthony. It was a great talk. We have a couple of minutes for questions, so let us know if anybody has any question.
If not, that's fine too.
I cannot see anybody here.
I'll ask a quick one, if I may.
Yes, of course.
Yeah, thank you, Anthony. Yeah, so these, let's say, paraconformities, more or less, like these stasis surfaces,
Yeah.
are these basically like geotechnical properties, the diagenesis of the surface, which is a function maybe of time or algae, is that something that you can sort of quantify? Because at some point, without morphology changing, you're not going to make any, let's say, surface traces because the substrate maybe is hardened a little bit. Still no deposition, no erosion, but now you physically cannot make any traces by, let's say, a crab moving along. Is that something that you can somehow quantify or detect?
I think that's something that's very difficult to accurately quantify, but it's something that you will have an idea of based on the depositional environment from your sedimentological interpretations. I think there'll be some settings where you might expect that to occur, and so you've got to be aware that that's a possibility, and others where it's far less likely. If you're looking at tidal deposits, that's not something you need to be concerned with. Whereas if you're looking at deeper marine deposits, then it's a caveat that should apply to every observation that you're making, that actually there is a possibility that we are recording this shorter duration. We're getting an accurate signal of ichnological activity from a short window at the start, and then we're not seeing anything after that because of this hardening of the substrate. And it's similar with paleosols, where you're getting this degradation of the surface, so you don't see signatures from earlier on. I guess it's the reverse almost. You're not seeing any of the earlier signatures because they've been degraded chemically, physically, and you're only seeing things from later on.
Right. So you're basically like Goldilocks effect, that for different sediments, but there is this substrate state that it's not right. It's not too hard, not too soft. That even in eolian settings with freezing, you can preserve sediments. You also have these conditions which supposedly just ideal, should be rare, and yet just by the volumes and numbers of traces, it seems like they're quite common. So we're lucky, like these conditions last long enough to record these traces.
Yeah. Well,
Yeah.
I'd say anything that we think should be rare, you've got to consider the number of occurrences that we've got worldwide. Right? Everything's so extensive that we're going to see examples of just about anything that can occur somewhere.
Sure. Thank you so much.
Of course.
We have a question in the chat. How can we determine the duration of stasis of a rock surface with ichnology?
So I think we need to accurately determining duration of stasis is difficult. Being able to say this lasted 3 hours. We're not going to be able to do that, but we can get broad ideas, and we're going to have to do that mostly from sedimentology. So depending on, well, I guess ichnology plays a part in determining depositional environment as well. But I think we don't want to put the cart before the horse almost. I think we want to have an idea of how long a duration of stasis was, how long the time window in which traces may have been formed based on sedimentological observations, so that then that can inform our ichnological observations. We don't want to be making a interpretation based on the ichnology and then using that to inform our interpretation of the ichnology, because then you end up with circular arguments. So I think the nice thing about ichnology is that it's such a neat mishmash of like biology and sedimentology. We need to understand both of them to be good ichnologists, and ichnology can inform sedimentology and sedimentology can inform ichnology. And I think we need a lot more ichnologists because it answers questions that no one else does.
Yeah. Renata?
Thank you, Anthony, for the nice talk. I would like to explore a little bit more an issue. It's well known for many years since Nora Nofka's work that microbial mats help a lot in trace fossil preservation. And then there is a kind of automatic interpretation that if you have a very well preserved trace fossils, so it must be a product of microbial mats in the substrate. Okay, so how to deal with this? I believe that many people that interpret true substrate also use the same analogy to explain the very nice preservation of ripple crests or even trace fossils. What do you think about it? It's all in all cases, microbial mats had a very important role in this preservation, or there are some cases in which we don't need microbial mats to play a role in the preservation of true substrates?
I think that microbial mats absolutely can play an important role in preservation of trace fossils, but also that they don't have to. I think that if you definitely can have deposition following a period of stasis without erosion. And that's really all you need to preserve anything in the rock record is, or anything on a bedding surface, is if you have if it's buried without being eroded. Microbial mats can be important. They can provide much better sedimentary conditions to preserve high fidelity traces, but you can also do that with the right kind of sediment composition of a substrate as well. If you have high clay content, for example, that can lead to really high fidelity preservation of highly yield traces. Microbial mats can also begin to hinder trace fossil preservation too, because once a mat gets thicker and more established, then it's a lot more difficult to imprint any trace upon it. And you can see examples of this. Oh, you can see modern examples of this where you can make a footprint in the sand, but if you're on a beach that's covered with microbial mat, then walking across it may leave no impression at all. So I think microbial mats are a double-edged sword. They can provide assistance to preservation, and they can lead to really great observations that we wouldn't get without the mats. But they can also hinder them too. I think that's the same with anything, that we need to account for them. If we observe evidence of microbial mats, then that should be reported alongside the trace fossils. But we shouldn't assume that every place we're seeing well-preserved traces, it's because of microbial mats if we don't see any other evidence of those microbial mats.
Thank you very much. I agree with you.
So, any other question? No? Well, I would like to thank Anthony for again for the talk and everyone for being here today. We are going to meet again next month. We in a new talk of this conversation series, and we are going to upload this talk probably next week on our YouTube channel. So if you want to watch it again, you will have it there. So thank you, everyone, and have a nice weekend.
Thank you very much.
Thank you. Bye-bye.
Bye-bye. Thank you.